All right, fantastic. Well, thank you very much, Sat, for the nice introduction. And thank you to the quantum design team, both in the UK and Italy, for hosting us today, and of course to the audience for joining us here. As Sat mentioned, we are a micro-XRF manufacturer out of Austin, Texas, and we've been involved in the energy dispersive spectroscopy industry for several decades, initially with EDS technology for scanning electron microscopes, and now heavily involved in leading standalone lab-based micro-XRF innovation. And our focused efforts are all around how can we help scientists create fast, high spatial resolution elemental maps, taking advantage of the physics of X-ray excitation, which allows the microanalysis across a large elemental range with high sensitivity. And that output is actually what we're viewing here. This is from a group at Queensland University in Australia studying, amongst many other things, plants that hyperaccumulate selective elements. And we see here the ability to spatially define regions of elemental accumulation throughout a plant and root body that provides insight on selective uptake pathways within different plants and soil types. And you can see the exquisite detail of where selenium in green, calcium in purple, and potassium in this pinkish red are located within these different plant structures. And the brighter the given color, the more intense or concentrated that given element is within that region. I should add that this group at Queensland University are also heavy users of the Australian synchrotron XFM facilities, and yet their workhorse tool is in fact a lab-based micro-XRF system generating data as shown on this slide here. So first, I'd like to briefly describe at a high level, what does a synchrotron provide? So synchrotrons are made up of a linear accelerator where an electron gun obviously produces electrons, which are accelerated to almost the speed of light. Then a booster ring is used to rapidly accelerate these electrons even further, which are then directed into a storage ring. And within the storage ring, bending magnets will alter the electron path, thereby producing photons, or what is known as synchrotron light. And these photons vary in energy from as low as 1 micro electron volt up to 100,000 electron volts. And so that is from the infrared region to up to hard X-rays. And as these photons are produced tangentially to the electron direction, these photons are directed into a number of experimental beamlines. And depending on the analytical application need, that will dictate what beamline these are directed into. So at an XFM or X-ray fluorescence microscopy beamline, X-rays will first pass through a monochromator in order to select those of specific energies, those X-rays of specific energies. And this production of monochromatic light associated with synchrotrons is actually quite advantageous, as the spectral background is minimized significantly as compared to excitation. Yes.
Sorry, is it possible for you to minimize the screen? I've just noticed that it's appearing. So if you click the arrow at the top on the organizer screen, yeah, perfect.
Sorry about that. Didn't realize that was showing on your side. So yeah, at an XFM beamline, we'll pass these through a monochromator, and depending on the X-ray excitation wavelength required. And the X-ray beam is then focused onto the sample with spot sizes typically ranging from 1 to 10 micron for a microprobe and 50 to 500 nanometers for a nanoprobe. The sample is then scanned through the beam in a raster pattern to produce spatially resolved elemental maps based upon the characteristic X-rays that are emitted from the sample. These fluorescing X-rays are quantified using a detector located either perpendicular to the incident X-ray beam or in a backscatter geometry, and accessible elements depend upon the configuration and capabilities of the beamline and the energy selected, but these range typically from 2 to 25 kilo electron volts, or from phosphorus to silver at their K energy transitions, and higher Z elements at the L energy transition levels. So in comparing synchrotron XFM to lab-based micro-XRF, there are a few high-level differences that impact data quality and overall productivity. For example, incident excitation X-rays, as I mentioned earlier, for a synchrotron are typically monochromatic with minimized spectral background, which again allows significantly better signal to noise as compared to most lab-based systems, which use polychromatic excitation X-rays. Having said that, there have been advances on this front for lab-based systems with the introduction of doubly curved crystals, or DCC, as part of the optics. Additionally, synchrotrons produce very intense radiation on the order of 10 to the 11th photons per second, as compared to lab-based systems with polycapillary focusing optics, which can produce on the order of about 10 to the 8th photons per second. And this has a big impact on fluorescing counts per second for analyzed materials, and ultimately on your overall sample mapping speeds. In effect, how long does it take to dwell on any given pixel to produce a quality spectrum with good counting statistics? Also, there are a handful of synchrotrons now offering advanced detection electronics known as MIEA array detectors, and these allow for extremely high photon processing rates, which also impacts counting statistics. Having said that, silicone drift detectors, or SDDs, are most commonly used at both synchrotrons as well as for lab-based micro-XRF systems, and the modern electronics associated with these SDDs also provide for extremely good counting statistics. Spot excitation diameters can be as small as 50 nanometers for synchrotron XFM beamlines. Because of this very high excitation flux that we mentioned earlier. However, most users at a synchrotron operate in the low micron range. For polycapillary focusing optics on lab-based systems, spot sizes as low as 5 microns can be achieved. And finally, accessibility is a major difference between centralized synchrotrons and lab-based systems. Everyone attending this webinar can appreciate the importance of immediate access to analysis tools and the constant need to pivot in science as new ideas and hypotheses present themselves. And when using synchrotrons, this can be almost impossible. When a scientist may have only 24 hours of continuous beam time access per year. And this is, even that is achieved at either very large financial expense or countless hours of competitive proposal generation, or both. However, in access to lab-based micro-XRF systems can be 24/7 as needed. So there are some very real performance differences between synchrotron XFM and lab-based micro-XRF, such as quantitation capability, spatial mapping resolution, and the time needed to acquire these elemental maps. However, the accessibility and high volume use afforded by lab-based systems may in many ways make up for these differences and still allow answers to scientific questions in a more timely, affordable manner. Additionally, the use of lab-based micro-XRF can be used to properly inform more effective design of experiment for follow-on synchrotron XFM use when it is accessible. So before we jump into comparative data between synchrotron XFM and lab-based micro-XRF, I want to provide a few slides describing what constitutes a lab-based micro-XRF instrument.